Hello, and welcome back to the course on University Physics 3. We are still on the ninth chapter for this course, and this is the second lesson for this chapter. So before we proceed, let us first review some concepts. So in the previous lesson, we have discussed about Faraday's law, which gives you the induced EMF due to a changing magnetic flux. So for a magnetic flux to change, it can be three things. It's either the magnetic field can change, it can increase or decrease, or the area can change, it can decrease or increase also, or the angle can also change. It can increase, decrease, or it can oscillate, just like in our previous example. So for this lesson, we will be talking about motional EMF. We have actually discussed this in the last example on the lesson on Faraday's law. So we'll just dig deeper and explain more clearly the physics behind motional EMF. So motional EMF is the EMF generated by a conductor moving in a uniform magnetic field. So there should be a conductor moving. So if you have an isolated conductor and you move it perpendicular to an external magnetic field, which in this case is going into the page. So what happens is there will be force. There will be a force acting on the atoms. So you will have V cross B. So the positively charged atoms will move upward, and V cross B, the negatively charged atom, will move downwards. So that's actually very wrong. Atoms that don't actually move downwards, but the electrons are actually the one moving around in a conductor. So the electrons leave their atoms, such as those atoms become, in this region, becomes positively charged, and the region where the electrons go to, those atoms becomes negatively charged. So this conductor is now a source of EMF. It has a positive potential here and a negative potential here, meaning it has a potential difference or a voltage. So if you want to know where is the positive and the negative potential for a moving rod, you just use V cross B. That's the force on a charge, V cross B. So V cross B in this case is, so this is the positive terminal. So if you connect this to a stationary conductor, then current can now flow because it now forms a loop in this case. And the motional EMF is actually this integral here, integral of V cross B dot dl, but we'll only focus on its magnitude, which is VBL. And we'll only focus on the case where the velocity is perpendicular to the magnetic field, and the velocity is also perpendicular to the length of your conductor. They're all mutually perpendicular to each other. So it's VBL. So we actually have obtained this result in the previous example. Okay, let's go directly to examples. So suppose the rod in the figure is 0.10 meters long, and it's moving at 2.5 meters per second, and the resistance of the loop is 0.030 ohms, and the magnetic field is into the page, and it has a magnitude of 0.60 Tesla. So find the magnitude of the induced EMF, induced current, and the force acting on the rod. So first, induced induced EMF. So the magnitude of the induced EMF is just VBL. So you have the velocity, it's 2.5, magnetic field 0.60 Tesla, the length is 0.10 meters, so the final unit for that is volts, and you will get 0.15 volts. Now for the second problem, induced current. Induced current is just EMF over the resistance, so you have 0.15 over the resistance is 0.030 ohms. So the final unit here is amperes, and you will get 5 amperes. So for the force on the rod, it's just IL cross B, and the magnitude of that is just ILB. Since the current through the rod is perpendicular to the magnetic field. So just ILB. Instead of ILB sine theta or sine phi, it's just IL times B. So the current is 5 amperes. The length is 0.10 meters. The magnetic field is 0.60 Tesla. The final unit of that is newtons. And you will get 0.30 newtons. So that's it. So for this problem, the induced EMF is 0.15 volts, the induced current is 5 amperes, and the force acting on the rod is 0.30 newtons. Okay, so another example. So in this case, the magnetic field is actually out of the page, and the loop, our loop here, contains a resistor. So this rod, since this is now moving, it becomes a source of EMF. So you have a source of EMF, we have a resistor, so it's now a complete circuit. It's a simple circuit. So the circuit shown, consider the circuit shown where the bar has a length of 0.360 meters. The resistance is 45 ohms, and the magnetic field is 0.650 Tesla. First question, is the induced current in the circuit clockwise or counterclockwise? Okay, so the magnetic field is outside, out of the page. So you perform a V cross B, so V, that direction, and B is out of the page. So the magnetic field, so the positive terminal is actually, the positive potential is actually this one. And this will be the negative potential. Meaning, if this is the positive terminal of your battery or your source of EMF, the current will move in a clockwise manner. So the answer for letter A is, it is clockwise. So the answer is clockwise. This one. Okay, letter B. At an instant when the resistor is dissipating electrical energy at a rate of 0.840 joules per second, what is the speed of the bar? So what do you mean by this rate? The resistor is dissipating electrical energy. What is that rate? Joules per second. So that is actually power. So joules per second is watts. So power. So power, we are given the power. It's 0.840 joules per second or 0.840 watts. And this is actually equal to I squared R. This is the power loss in the resistor. Power dissipating means lost. This is the power loss in the resistor. So we can actually solve for the current. And from the current, we can solve for the EMF. And from the EMF, we can solve for V. So the current from here is actually just square root of P over R. That is our current from this equation. And since the EMF is just current over resistance, and this is equal to VBL, therefore I can solve for V now. Velocity is just I over BL R. And since I is equal to P over R, so you have square root of, there's an R in the denominator, so square root of P over R, and then 1 over BL. Sorry, I made a mistake. This is Ohm's law. This is I times R. This is I times R. So therefore, V is just IR over BL. IR over BL. That one. So you have I times R over BL. So you have r in the numerator, you have square root of r in the denominator, so you will have square root of p times r over v L. So this is our velocity now. So we just need to substitute the values. So it's square root of the power 0.840. The resistance is 45 ohms over B, magnetic field magnitude 0.650 times the length, which is 0.360. The final unit of this should be meters per second if you converted all your units to standard SI units. And you will get a value of 26.3 meters per second. So that is now the velocity. Okay, it's a slightly challenging problem. So the current is clockwise and the velocity magnitude is actually 26.3 meters per second, but that is only at that instant where the power is 0.840 joules per second. Okay. Okay, this is the last example, and this is a very, very challenging problem. So this is what we call a railgun. Okay, so a bar with length 0.80 meters is free to slide without friction on a horizontal rail. There is a uniform magnetic field of 1.5 Tesla directed into the plane. At one end of the rails, there is a battery with EMF 12 volts and a switch. The bar has mass 0.90 kilograms and resistance 5 ohms, and all other resistances in the circuit can be ignored. The switch is closed at times t is equal to 0. Okay, so first problem or question is sketch the speed of the bar as a function of time. And letter B, just after the switch is closed, what is the acceleration of the bar? Letter C, what is the acceleration of the bar when its speed is 2 meters per second? And letter D, what is the terminal speed of the bar? So this is actually a very challenging problem. So this is reverse of the motional EMF. So motional EMF is you pull the bar so that you can have EMF. But here, you supply it with the EMF so that the bar will move. So it's the reverse. So it's a rail gun. Okay. So at time is equal to 0, when you close the switch, current will flow through the bar downwards. So there will be a current here. At time is equal to 0, there will be a current flowing downwards. This is, say, I naught. And then the bar will now start to move from a zero speed to a certain speed. So since the bar is now moving here with a velocity v, meaning v cross b, magnetic field is inside, the upper part of the bar will now become a positive terminal or positive potential, the lower is negative terminal. So meaning the current, there will be now an induced EMF, an induced current in the loop. So I naught is a clockwise loop, but the induced EMF is a counterclockwise loop. So there will now be two currents flowing through our loop, I naught and I. Okay, so this current, the current I naught will actually exert a force on the bar. So you have I cross B, so this will be F naught. And this current, I cross B, there will be a force also in the opposite direction. So at the start, at time is equal to 0, only this current is present and only this force is present, meaning the bar is accelerating. The net force on the bar is just F naught. So the speed of the bar, letter A, speed of the bar as a function of time will somewhat look like this. So at time is equal to 0, its velocity is 0, but it will spike up. But then there's a force in the opposite direction, so it will no longer increase its velocity. It will slow down a bit until when the two forces become balanced, the velocity becomes constant. So that one, this is the speed of the graph as a function of time. So initially, when there's only the original force present, it's accelerating, its speed is increasing, but then there's an opposite force in the opposite direction, so it will try to slow down. And then when the two forces are now balanced, so this speed now is what we call the terminal speed. And this is actually the last question for this problem, the terminal speed. The two forces are equal, meaning the bar is no longer accelerating, it's now moving at constant velocity because it no longer has acceleration. Okay, so this is for letter A, that's the plot. Okay, so for letter B, just after the switch is closed, what is the acceleration of the bar? So this is letter A. So for letter B, just after the switch is closed, the net force on the bar is just F naught, the original force. And the original force is just I naught LB. So IL cross V. And this is equivalent to the mass of the bar times the acceleration of the bar, initial acceleration of the bar. So you can now solve for the initial acceleration of the bar. So I naught here is just the original EMF over the resistance. So we will have epsilon naught LB over R is equal to mass. So I'm just divide both sides by M. So this is now the acceleration of the bar at time is equal to 0, just as you close the switch. So this is 12 volts. L is also given, it's 0.80 meters. Magnetic field is also given, it is, what is the magnitude? 1.5 Tesla. The mass is also given, 0.90 kilograms. The resistance is also given, it's 5 ohms. If you substitute all of that, you will get a value of 3.2 meters per second squared. So meaning its speed will increase by 3.2 meters per second every second. So if it starts from 0, such as in this scenario, so it starts from 0, after 1 second, its speed will now become 3.2 meters per second. After another second, another 3.2, so 0, 3.2, then 6.4, and so on. That is the acceleration. But after the switch is closed, there's now an opposite force in the opposite direction. So what is now the acceleration of the bar when the speed is 2 meters per second? So in this case, in letter C, the problem now is this one. So the net force now is F naught minus F. So this is now the net force. There's a force to the right, which is F naught. There's a force to the left, which is F. This should be equal to the mass times the acceleration. So F naught is just I naught LB. F is just I LB. So there are two currents, I naught and I. And this is equal to mass times acceleration. So of course, I naught is the original EMF over R, LB. So we can actually factor out LB here. So you will just get I naught minus I. So I naught and I is just the EMF over R. So the EMF is just actually VBL. So this is motional EMF over R. So this is I, VBL over R, the motional EMF over the resistance. And we factor out that with LB or BL. This is equal to mass times acceleration. So we solve for V. So from this equation, we solve for V. This is actually, we solve for A because V is actually given in this problem. The speed V is 2 meters per second. So solve for A. So A will now be equal to BL over M. Okay, they both have a common factor R. We can actually factor that out. So BL over R. Then you have epsilon naught, the original EMF, minus VB. So these quantities are already given. So you substitute all of that and you will get a value of 2.6 meters per second squared. So the acceleration is actually decreasing from the original acceleration of 3.2 meters per second. After this time, it now becomes 2.6 until such time that the acceleration will become 0 and the two forces are balanced. So that's actually for the question for letter D. What is the terminal speed of the bar? So in letter D, in that case, the net force, which is F naught minus F, is actually equal to 0. So the two forces are now equal. So this is just I naught LB minus this is ILB. This is equal to 0. Therefore, these two terms are equal. They're all equal. So divide both sides by LB, so meaning I naught is equal to I. So divide both sides by LB, so meaning I naught is equal to I. So I naught is just epsilon naught over R. I is just EMF, induced EMF, which is VBL over R. So multiply both sides by R and you get B is just equal to epsilon naught over BL. That's all. So 12 volts, this is 12 volts, this is 1.5 Tesla, this is 0.80 meters. And you will get a value of 10 meters per second. This is now the terminal speed, which is this speed, the terminal speed of our bar. So initially it's accelerating, but its acceleration is actually going down, decreasing, until its acceleration becomes 0, meaning constant velocity. So that is the terminal speed. Terminal speed meaning is the final speed, the terminal, the end speed. Okay. So that is the end of this problem. And basically the end of this lesson. So in a real scenario, railguns are actually used as weapons. So usually they attach, so this is the bar, no? They attach something to the bar, so that attach something will be your projectile that will be projected, or that will go out of the gun. So basically that's your bullet or your projectile. So usually improvised rail guns are used by our local fishermen. So they use a rail gun to spear a fish. Okay. So that is the end of this lesson. So in the next lesson, we will be generalizing all of the equations in electromagnetism, and they're actually collectively known as the Maxwell's equation. So we'll now try to wrap up the concept of electromagnetism, the theory, the basic foundations of electromagnetism in the next lesson. So I will see you again in the next lesson.